All right, so recall that last time we finished talking about some properties or conditional expectations. And then we said that, given that we don't have too much time, we will be touching upon several topics. So unfortunately, the coverage will not be too detailed. That is regrettable. Um, but hopefully we'll talk a little bit about various things. So the couple of things I have on my mind are, one is limit theorems. Limit theorems, you know, these are basically asymptotic results when you have a large number of random variables. We saw that there are at least two types of limit theorems, namely laws of large numbers and central limit theorems. We saw that in laws of large numbers, there's a weak law and a strong law, and these two have to do with the notion, the sense in which you have convergence. We've already seen a weak law of large numbers for L2 random variables, and so the idea last time was that we should at least see one strong law of large numbers. So that's what we're doing now. We're doing a strong law of large numbers. We're making some pretty strong assumptions on the random variables, and those assumptions can be weakened. Of course, to do that, the proof gets harder, but this way, at least we've seen one strong law of large numbers. So I want to pick up over there. Also, after this, I want to talk a little bit about a class of stochastic processes called martingales. You can get a lot of mileage out of martingales, and there are a lot of beautiful connections with many parts of analysis, whether it's martingales in discrete time or continuous time. Again, we will unfortunately only be able to just skim the surface. I want to do that right away because we have just done conditional expectation, and that is hopefully fresh in your mind. Once that is done, once that is done, as in once we talk a little bit about martingales, I'm hoping we can spend some time talking about the tools and techniques to prove central limit theorem. All right, so that is kind of the plan. Now, I know that there is one lecture that we have to make up. And given that things are going to get rather tight, I'm thinking that I will have this as recorded lecture. So I will record the lecture and share that with you. How does that sound? Anybody? Somnath, if you said something, I didn't hear it. Works with me. Okay, thank you. All right, so that's what I'll do. Of course, the other three lectures, we'll of course have it in class. So the advantage of in class is you can stop me and ask questions. But I think if it's one lecture which is done asynchronously, namely if one lecture is done recorded, that should be okay, I think. So that is the plan. Then we want recorded lecture. Of course, next week we will have lectures as usual. Again, I will be giving a couple of assignments, I think, to do. I know I still have to return your old assignments. I haven't forgotten. My apologies. I've been a little delinquent on that front. Anyway, so let's get started. So let me go ahead and turn off the video. And let me go ahead and share the iPad screen with you. All right. So we're trying to prove a strong law of large numbers. Okay. So here we're saying, suppose that x1, x2, and so on are independent random variables. Okay. And we're going to assume that they're actually in L4, namely the fourth moment exists. And actually, we're going to assume a little more than that. And suppose that for some constant k in 0 infinity, expectation xj to the 4 is less than or equal to k for all j. Then you want that E of xj is 0, namely the random variables have mean 0. Then you let Sn be the sum, I going from 1 through n xi. Our result here states that 1 over n Sn converges to 0 with probability 1. Okay, so we are most of the way through the proof. What did we do? We looked at Sn to the 4. We got this term plus this term plus other terms. Okay. Then last time we said that I'm going to end up taking expectation on both sides. Then we saw that expectation of other terms is going to be 0. So expectation of this will survive, expectation of this will survive. That's what you have right here. Once I take expectation on both sides and the expectation of other terms is 0, this is what you're left with. Then you use a fact, this is called monotonicity of LP norms. So basically what you're saying is, suppose that P is in 1 infinity, infinity excluded, for right now at least, the bigger P gets, the bigger the P norm of X gets. So if you fix an X and you keep making P bigger, the norm is only going to get bigger. Anyway, we use this fact to get this claim. And then finally, we have found, we have worked our way to the following. We have, so then we got an estimate expectation Sn to the 4 equals this. Then we figured out, okay, so this guy is no more than k, we pull the k out. This guy is no more than k, we pull that k out. And then we had to just calculate these simple sums. Once all the dust settles, what you get is this. Expectation Sn over n to the 4 is less than or equal to 3k over n squared. And now you look at the right side and you say that, hey, the right side is a series which decays like 1 over n squared. So this is summable. So sum n going from 1 to infinity of expectation Sn over n to the 4 is less than or equal to 3k times summation n going from 1 to infinity 1 over n squared. And this guy, of course, is finite, right? Because the power of n is 2. Okay, so we're almost done. So what can you say? Now, by the way, we studied this when we did monotone convergence theorem. All right, so we did something like this. Suppose I have a sequence fn, which is greater than or equal to 0, and I'm taking the integral of the sum of fn. That is going to be just the sum integral fn. Okay, and here fn is greater than or equal to 0. I'm going to use that fact right here. These guys are like my fn's. This expectation is my integral, and here I have a summation. So summation of the integral of a bunch of non-negative quantities is going to be the same as the integral of the summation of the non-negative quantities. Okay, so this is just monotone convergence theorem. So by monotone convergence theorem, or perhaps more accurately, and its consequences, right? So we made a statement about this. We made a statement that integral sum fn is the sum integral fn whenever all the fn's are in L plus. This is something we have done and proved. Okay, for fn in L plus, integral sum fn is sum integral fn. Okay, so and that's what I mean. That's what I'm referring to when I say and its consequences. The monotone convergence theorem and its consequences we have. So here I have sum of the expectation that is going to be the same as expectation of the sum n going from 1 to infinity Sn over n to the 4. This equals the sum n going from 1 to infinity expectation of Sn over n to the 4. And this we just saw is less than or equal to 3k summation n going from 1 to infinity 1 over n squared, which is finite. All right, so what do we have? Thus, expectation of sum n going from 1 to infinity Sn over n to the 4 is finite. And now we will say this guy is a non-negative entity. If the expectation of this non-negative function is finite, that means this non-negative function must be finite almost surely. So this was another thing we did in integration. We said if f is an L plus and integral f is finite, then f is finite almost everywhere. Okay, so this thing that I've written in the corner, this is something we did when we talked about measure theory. If f is an L plus and integral f is finite, then f must be finite almost everywhere. So that's the principle I'm going to use here. This is my f. This expectation is my integral. And so I'm saying if the integral of f is finite, then f must be finite almost everywhere. So, hence, sum n going from 1 to infinity Sn over n to the 4 is finite, P almost surely, right? Again, it's probability, so we say almost surely rather than almost everywhere. The idea is the same. And now you say, wait a second. I learned in my BSc that if an is greater than or equal to 0, and if the sum n going from 1 to infinity, an is finite, then an must go to 0 as n goes to infinity, right? This is something you would have learned in your BSc, right? Suppose I have a sequence, a non-negative sequence. If that sequence is summable, then the nth term goes to 0 as n goes to infinity, and that's what we're going to use here. So thus, P almost surely, what do you have? P almost surely, you have that this series is finite. Well, that another way, okay, so P almost surely this series is finite. Well, if the series is finite, then certainly the nth term must go to 0 as n goes to infinity. So then P almost surely we have Sn over n to the 4 goes to 0 as n goes to infinity, and we're done. Right? So basically it is saying that Sn over n goes to 0 as n goes to infinity. And this is the idea we're using. Okay? We're using the idea that if I'm summing a non-negative series and I get something finite, then the nth term must go to 0 as n goes to infinity. Again, if you want, we can say i.e. Sn over n goes to 0 as n goes to infinity, P almost surely. Right? Which means you can throw away a null set, and once you throw away this null set on whatever is left, Sn over n goes to 0 as n goes to infinity. In other words, you have proved this strong law of large numbers. Any questions with this? Questions? Okay, so if you go back and look at it, you will realize that we nowhere did we use identically distributed. That's why the statement of this strong law of large numbers did not say anything about identically distributed. We did need to assume that expectation xj to the 4 can be bounded above by one single constant k, which works for all xj's. That we did have to assume. Yes. Independence we did need. Yes. All right. Of course, this can be weakened. All right. So this is obviously not the last word in strong law of large numbers. You can weaken some of the requirements, and you can basically just do this for id random variables, which are just in L1. Okay. Of course, you have to work harder. All right. Any questions with this? Okay. So the next thing I want to do is I want to plug in one hole in here, and that hole is right here. We said that if omega fp is a probability space, and suppose x is an LR omega fp for each r, and if p is bigger than q, then the LP norm of x is going to be greater than or equal to the LQ norm of x. So let's fill in that gap. So this is the proposition. So this is monotonicity of LP norms. Right, by the way, we have already used this. All right, so let omega fp now be a probability space. And suppose x is in LR of omega fp. If you're wondering why I haven't used p, it's because I want to use p for something else. For each r in the interval closed at 1, open at infinity. Okay, so basically I'm assuming that x is an LR for any r finite. Then for 1 less than or equal to q less than p, we have norm x in LQ is less than or equal to norm x in LP. All right, so I think maybe it's better to move this to the next page, because otherwise we'll start here and then the proof will start on the next page. So let's move this to the next page. All right, much better. All right, so this is the claim we want to prove, the monotonicity of LP norms. Anyone want to make a guess as to how we'll do this? Anyone? No? Okay, so let's do the following. Actually, I am kind of tempted to leave this for you to fill in because this is a nice application. Have you seen this before, by the way? Anybody there?
Yeah, if a domain is bounded, then
No, but here, okay. So one second. So here you're in a general probability space. So boundedness has no meaning, right? On the real line, you can take a subset and ask whether it's bounded or unbounded. In the metric space, you can ask whether a subset is bounded or unbounded. But in omega, there is no sense of what bounded or unbounded is.
we have seen that norm equivalence in bounded domain. I think that LQ is contained in LP.
Okay. By the way, here, what is the argument? Okay, LQ is contained in LP, but have you seen this relation among the norms? Namely, that the LP norm is bigger.
No.
No. Okay, so let's see how you go about doing this. So let 1 less than or equal to Q less than P. All right, what do we want to show? We want to show that the LQ norm of X is less than or equal to the LP norm of X, right? So what do you want to show? You want to show that LQ norm of X is less than or equal to the LP norm of X. Equivalently, you want to show that if I take the LQ norm of X to the qth power, that is going to be less than or equal to the LP norm of X to the qth power, right? This if and only if this. All right. So now let's start with this one. Let's start with this one. Let's start with this quantity. So I look at norm X in LQ to the Q, right? So what is this going to be? This is going to be expectation absolute value of X to the Q, right? Now what I'm going to do is I'm going to say, wait a second, this is just expectation absolute value of X to the Q times 1. Okay, so now what I'm going to do is I'm going to start thinking in terms of Holder's inequality. All right. All right, so now what I'm going to say is the following. Now, expectation absolute value of X to the Q to the P over Q. By the way, this is just expectation absolute value of X to the P. This is finite. Do you agree with this? Yes or no? Okay, so if I take absolute value X to the Q and I take it to the power P over Q, then I'll get absolute value of X to the P. And expectation absolute value of X to the P is finite because we know that X is in LP. So expectation absolute value X to the Q to the power P over Q is finite. So absolute value of X to the Q is in L P over Q. Any questions with this? All right. Now let's find the conjugate exponent of P over Q. What is the conjugate exponent? That means, what do we want? We want that 1 over S plus 1 over P over Q, which is Q over P, is 1, right? I say two numbers, L and M are conjugate exponents, so 1 over L plus 1 over M is 1. Okay, so what has to happen here? This means I have to have 1 over S is 1 minus Q over P. This ends up being P minus Q over P. And so you get that S must be P over P minus Q. Any questions so far? So thus, P over Q and P over P minus Q are conjugate exponents. Any questions with that? Okay, so now what I'm going to do is I'm going to come to this thing and I'm going to use Holder's inequality. Okay. Let me write down what I have again. Norm x LQ to the cube power is expectation, absolute value of x to the q times 1, right? And now I will say that this guy belongs to L P over Q. I have checked that right here. Okay. Actually, let me just make it abundantly clear that I'm not talking only of absolute value of x, but absolute value of x to the cube. Okay, so absolute value of x to the cube belongs to LP over Q, and 1 belongs to L P over P minus Q. Do you guys agree with that? Now I will come back to Somnath. So Somnath, basically your intuition was right. You were thinking of a bounded set. Basically what I think you were thinking about was finite measure. That is the key thing. Here, this whole thing works because you're dealing with a finite measure. Okay, so I want to say a couple of things. Suppose I replace this thing with measure mu, which is finite. Okay. This thing will get modified a little bit. Okay, it won't be exactly the same. It's working out beautifully here because the measure is not just finite, but the measure is 1. But I think, Somnath, maybe that's what you were thinking of when you thought of bounded, because perhaps you were thinking of a Lebesgue measure. And of course, if you're talking about Lebesgue measure and you're talking of a bounded subset of Euclidean space, that is going to have finite Lebesgue measure. All right, any questions so far? All right, so now I'm going to use Holder's inequality. So absolute value of x to the q is in LP over q. The constant function 1 is in LP over P minus q. So by Holder's inequality, the product must be in L1. So by Holder's inequality, the product, now remember, the product of anything with 1 is just the thing itself. So the product mod x to the q must be in mod x to the q times 1. This must be in L1. And what must be true? What you must have is that the expectation of mod x to the q is going to be less than or equal to, I'll take mod x to the q, and then I'll take its norm in P over Q, and then I'll take 1 and I'll take its norm in P over P minus Q. Any questions with this? This is just a straightforward application of Holder's inequality. All right. Mod x to the q is an LP over q. 1 is an LP over p minus q. P over q and p over p minus q are conjugate exponents. So by Holder's inequality, this guy times this guy is an L1. Now that is old news. You already knew that. But the other part of Holder's inequality is useful. So by Holder's inequality, the product, this thing is an L1. You already knew this. But what's more interesting from Holder's inequality is that the L1 norm of this guy, which is expectation mod x to the q, is less than or equal to the p over q norm of mod x to the q times the p over p minus q norm of the function 1. Any questions? Okay. Where am I? Right here, right? Okay. Okay, so now let's see what we get. So expectation, absolute value of x to the q is going to be less than or equal to what? So I'm going to take the p over q norm of mod x to the q. Actually, let me just rewrite that. So I'll take mod x to the q, and then I'll take its p over q norm, and then I'm going to take the function 1, and I'm going to take its p over p minus q norm. Right? Now let's see what these guys are. So the first guy is going to be what? I'm going to take mod x to the q, then I have to take its p over q norm. So what should I do? I should exponentiate it to the power p over q. Then I should take expectation, and then at the end I should take 1 over p over q, so I should take q over p. Right? And what should I do for the other guy? If I raise 1 to any power, I'll just get 1. So I'm going to basically take expectation of 1, and I'm going to raise it to the reciprocal of p over p minus q, which is going to be p minus q over p. Any questions so far? All right, now remember that this whole thing is just 1, right? You're dealing with a probability measure. So this equals 1 since probability measure. So note that if you were dealing with a finite measure, which was not a probability measure, this particular term would not beautifully end up being 1. It would be constant, but it would not just be so nice and cleanly 1. But here it's just 1. And then what do you want to get? So this is going to equal. All right, so here I'm going to have expectation of, now if I look at this, this is mod x to the q to the p over q. So this is just mod x to the p. Mod x to the p. And this whole thing is to the power q over p. Right, and so now we're kind of done, right? So because I have expectation mod x to the q, okay, actually let me do the following, less than or equal to this. Any questions? Now I'll just take pth roots. Okay, here I should let me put another bracket just in case there's any confusion. Okay, now I'll just take qth roots on both sides. So take qth roots to get expectation mod x to the q, the whole thing to the power 1 over q is less than or equal to expectation mod x to the p to the q over p, and I'm taking the qth root, so I'm going to get this is to the power 1 over p. But what is this saying? This is saying precisely that the LQ norm of x is less than or equal to the LP norm of x. All right, so this is the monotonicity of LP norms that we had said. So once again, in a probability space, LP norms, you will have monotonicity. If you have a finite measure space, okay? If you have a finite measure space, you will have something like this, norm FQ less than or equal to norm FP, and then you'll have the measure of the whole space to the something, I forget what it is, so it's some sort of formula C of PQ. Okay, so I don't remember what it is. Some expression involving P and Q. Okay. I want to say it may be 1 over Q minus 1 over P. I'm not sure. But anyway, you can easily compute it. Okay, this is not rocket science. Okay, this is easily computable. Actually, you can tell from here what, perhaps you can tell from here what, you can just play around and figure out what it's going to be. So in a finite measure space, this is what you're going to have. Norm fq is less than or equal to the norm fp times mu omega to some power involving p and q. I forget what it is. I will leave it to you to figure out. Just play with this example, modify it. Assume that instead of a probability space, you had a finite measure space. Then maybe instead of x, you might write f out of habit because it's a measurable function. You can go through this same calculation and you can basically convince yourself that a relation of this type is true. And I'll leave it to you to figure out what C of P over Q is. Any questions with this? Okay, so I'm inclined to leave all this scribbling on here because I think this may be helpful. It doesn't look pretty, but okay. No. Okay. Where is that? Okay. This much, it doesn't look too bad, right? Okay. So this looks reasonably clean. So let me just leave that. So if finite measure space omega fp and f is an LR for each r in 1 infinity, then for 1 less than or equal to q less than p, we have this thing. Okay. I'll leave it to you to figure out what C of P over Q is. I think it ends up being 1 over Q minus 1 over P, but I may be wrong. Questions? All right, so that takes care of this strong law of large numbers. So now I want to say a little bit about stochastic processes. The thing is that this is an important enough topic, and this is something that leads to further study in probability. So I think it is good to talk a little bit about stochastic processes. So let's see what stochastic processes are. We will basically be focusing on discrete time stochastic processes. And one example that I want to just play around with a little bit is the example of martingales. Okay, so first question is, what is a stochastic process? Right? So here's the answer to that question. So let omega fp be a probability space. All right, so what do I mean by a stochastic process? Okay, now there are a couple of different types of stochastic processes. There are so-called discrete time stochastic processes. There are also so-called continuous time stochastic processes. Right now, we're going to talk about discrete time. So discrete time stochastic process on omega fp is an indexed collection of, well, it's an indexed collection x equals xn, n in z plus. It's an indexed collection of random variables taking values in some measurable space. Okay, so remember a couple of things. First of all, we have almost always been dealing with real valued random variables, but if I'm not much mistaken, we basically said that a random variable is no more, no less than a measurable function, which means to talk about a random variable on the domain and range of the function, you need to have a sigma algebra. Okay, so that means you could talk about a random variable taking values in an arbitrary measurable space. That space need not have any structure like the real line or the complex numbers or anything like that. So you can talk about a random variable taking values in just some measurable space. Okay, so what is a discrete time stochastic process? Well, it's just an indexed collection of random variables. So what is the index here? The index here is n. Okay, and in the case of stochastic processes, we'll think of this index as time. Okay, well, I'll write that out kind of nicely. So what is a stochastic process? It is simply an indexed collection of random variables. In case of discrete time stochastic processes, your indexing parameter, which you typically denote by n, takes values in z plus. So it takes values 0, 1, 2, 3, and so on. And you interpret n as time. So you basically think that you have some system evolving in time. It's evolving randomly, and the state of the system at time n is given by the random variable xn. Okay, so just a couple of quick notes. So here, n is interpreted as time. Okay, and the sequence xn, n greater than or equal to 0, describes the time evolution of some random phenomenon. Okay, so we will almost always focus on the case where S is the real line. So you don't have to focus, but we'll focus. So we'll focus on the case when S is the real line and script S is just the Borel sigma algebra. Okay, so that's what we'll focus on. Any questions for this? So if you're wondering what an example might be, so here is an example. I'm going to start labeling the days. 20th November will be day 0. 21st November will be day 1. 22nd November will be day 2. 23rd November will be day 3, dot, dot, dot. Actually, I'm going to be a little more precise. 12 noon on 20th November is going to be time 0. 12 noon on 21st November is going to be time 1. 12 noon on 22nd November is going to be time 2. 12 noon on 23rd November is going to be time 3. I'm now trying your patience, but now here's what I'm going to do. At time n equals 0, n equals 1, n equals 2, n equals 3, dot, 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 I will go to the internet and I will look at the price of the stock of Larsen and Toubro. And I will record that as my random variable xn. So x0 is the price of the LNT stock on 20th November at 12 noon. X1 is the price of the LNT stock on 21st November at 12 noon, dot, dot, dot. So this you can think of as a discrete time random process, okay? Because you're fixing the time, you're saying every day at 12 noon is when I'm going to go look at the stock price. The stock price changes randomly. If you know how it changes, please let's talk offline. Usually most people assume that it changes randomly, but if you have insider information, it's always good to know. But anyway, generally accepted that the stock prices varies randomly. And so here you can think of xn as being the stock of a certain company at time n. And here time n takes discrete values. And one way to do that would be you do it maybe every hour if you like, or you do it every day at a certain time or something like that. Okay, so if you want an example, that's what you should think of. Okay, so now the next thing is we also want to talk about a new animal called a filtration. Okay, so let mega f p be a probability space. So what is a filtration? So a filtration is an increasing family Fn n greater than or equal to 0 of sub sigma algebras of script F. All right. So what does this mean? Let's just make sure. I.e. 1 for each n greater than or equal to 0, Fn is Fn is a subset of F. 2 for each n greater than or equal to 0, Fn is a sigma algebra. And 3 for each n greater than or equal to 0, Fn is contained in Fn plus 1. Okay, so this thing that I'm now enclosing in square brackets is just explaining what this phrase means: increasing family of sub-sigma algebras of F. So what must be true? This is a family such that for each n, Fn is a sigma algebra. Now they said sub-sigma algebra of F. That means for each n, Fn is subset of F. And then they said increasing. Now increasing, of course, with respect to set inclusion. So for every n greater than or equal to 0, Fn subset of Fn plus 1. Any questions with what this is? Okay, so here basically you're just looking, you're looking at a family of sigma algebras indexed by the same time parameter n. Okay, so note that the time parameter there and the time parameter there are one and the same. And these guys are all sub-sigma algebras of F. So each of them is a sigma algebra, each of them is a subset of F, and they're increasing. That means as n gets bigger, Fn cannot get smaller. Which means for n greater than or equal to 0, Fn plus 1 must definitely contain Fn. Okay, so what does this represent? Now, this we have kind of hinted at. We've said that in probability, sigma algebras correspond to information. So what is the intuition here? So filtration represents accumulation of information as time increases. Okay, that's why it has to be an increasing family, because the idea is that Fn is the information available to an observer at time n, and we're assuming that the observer does not forget anything. So whatever information the observer has at time 4, they definitely have at time 5 and 6 and so on. Okay, and so here we interpret Fn as info available to an observer at time n. So now you may ask the question, what does it mean? If I say Fn is the info available to an observer at time n. What does this statement mean? Fn not as is. Okay, if I make the statement Fn is information available to an observer at time n, what does this mean? That's my question. And here's the answer. The answer is, for any event A in Fn, the observer knows at time n whether or not the event has occurred. In other words, if I take A in F3, okay, and I go to the observer at time 2, and I ask them, has the event A occurred? At that time, they may not have enough information to answer the question. If I go to them at time 3 and I ask them, has A occurred? They can tell me, yes, it has occurred, or no, it has not occurred. And of course, if I go to them at any time 4, 5, 6, and so on, and if I ask them, has the event A occurred? They can tell me, yes, it has occurred, or no, it has not occurred. So when I say that the observer has access to the information Fn, that means if at time n you go to the observer and you ask them, has this event A belonging to Fn occurred, they can tell you, yes, it has occurred, or no, it has not occurred. In other words, they can answer the question. Now, of course, the idea is they're not forgetting. So as time goes on, you can also ask them at time n+1. So you can ask them at time F4 whether A has occurred with A in F3, and they'll still be able to answer the question. Any questions with this? Okay. So then here's another, while we're throwing some terminology, let's throw in one more definition. I'm going to define something called a filtered probability space. And a filtered probability space is just a probability space equipped with a filtration. That is it. So if omega Fp is a probability space, and Fn, n greater than or equal to 0, is a filtration, then we refer to this object, omega Fn P, as a filtered probability space. So to put another way, a filtered probability space is just a probability space equipped with a filtration. Any questions so far? While we're throwing definitions, let's throw a couple more. I want to now define what it means for a stochastic process to be adapted to a filtration. Okay. So let x equals xn, n greater than or equal to 0, be a stochastic process defined on the filtered probability space omega. Well, let me actually be a little more explicit on. Well, you know what filtered probability space is. So on omega Fn P. All right. By the way, this is just, you could, instead of saying this, you could have broken it up and said omega Fp is a probability space and Fn is a filtration on it. This is just writing everything in short. I'm saying omega Fp is a probability space and Fn is a filtration on it. Okay. So let x equals xn be a stochastic process defined on omega Fn P. Okay, I want to define what we mean by adapted. So the process x equals xn, n greater than or equal to 0, is said to be adapted to the filtration Fn or we may say Fn adapted if for each n greater than or equal to 0, xn is Fn measurable. All right, so that's what I mean by a stochastic process being adapted. So I have um, omega fp, which is a probability space. I have fn, which is a filtration on it. In other words, omega fnp is a filtered probability space. I have x equals xn, which is a stochastic process defined on it. I will say that the process x is adapted to this filtration. Another way of saying that briefly is to simply say it is fn adapted if for each n greater than or equal to 0, xn is fn measurable. So now what does this mean? Okay. So note, if x is fn adapted, then for each n greater than or equal to 0, xn is fn measurable. Okay, nothing new there. Thus, for each n greater than or equal to 0, for each a in B of R, the event xn element of A equals xn inverse of A is in Fn. Right, what does measurability mean? Measurability means for any Borel set, if I take the inverse image onto the mapping of that set, the result will be measurable, right? So what does this mean? This means that for any n greater than or equal to 0 and for any Borel set A, if I look at the event xn falls in A, also written as xn inverse A, this is in Fn. In other words, if you are to ask an observer, has xn fallen in such and such set? If x is adapted, then they can answer the question and they can say yes or no. Thus, for any n greater than or equal to 0, A in B of R, the observer with information Fn knows whether or not xn in A has happened. In other words, the observer knows whether or not xn has fallen in A. So if you ask the question, has the xn fallen in A, the observer can tell you yes or no. All right, so I think I've thrown quite a few definitions at you. So let me stop sharing here. I think I've thrown quite a few definitions at you. And I think sometimes, at least when I'm learning something new and somebody throws too many definitions at me, I need some time to go back and kind of process it. Now, maybe you have already processed it, and if you've done that, good for you. But I'm thinking I'd like to stop right here. There are a couple more definitions to throw, but I want to give a chance for this material to crystallize before I throw more stuff at you. So I'll go ahead and share the notes. Any questions?